All right, let's get right into it and unlock the ASME codes. Whether you're on site, in the design office, or running QA/QC, this is your complete practical guide to really mastering the standards that keep our entire industry safe and running smoothly. So think about this for a second. It's a pretty serious question, right? We're surrounded by high-pressure boilers, massive vessels, complex piping systems. What's the invisible shield that's actually protecting all of us from a potential disaster? Well, the answer is a set of rules. It's a universal language spoken by engineers all over the world. And that's where the ASME codes come in. You can think of them as the ultimate engineering playbook. They give us the absolute minimum safety requirements for pretty much everything, from a simple air tank all the way up to a nuclear reactor vessel. They ensure that integrity is baked in from the very first sketch to the final pressure test. So here's our game plan. We're going to start with the fundamentals. Then we'll break down the specific codes for boilers and vessels. After that, we'll cover the core pillars of quality, materials, and welding. And then we'll take a quick look at the super high standards of nuclear. And to wrap it all up, we'll put everything together into a practical site workflow that you can literally use tomorrow. Okay, let's dive into our first section. Before we get into all the specific formulas and site checks, we really need to get our heads around why these codes are the absolute bedrock of safe and reliable engineering. And that why is absolutely everything. Look, these codes aren't just about tedious paperwork. They literally protect lives and billion-dollar assets. They create a universal standard, right? So an engineer in Houston and an engineer in Dubai are working from the exact same safety principles. They give us a clear, repeatable method to verify that the materials are right, the fabrication is solid, and the final installation is safe. It's a huge deal. All right, let's start getting into the nitty-gritty, starting with the equipment that handles pressure. This is where the risk is highest and, honestly, where the rules are most critical. We're talking boilers and pressure vessels. First up, we've got ASME Section 1. This is for power boilers, the real high-pressure workhorses you see in power plants. The key thing to understand here is the Hope stress formula. So why this one? Well, because it directly calculates the force that's trying to rip the boiler's shell apart from the inside out. It is the fundamental check that proves the wall thickness can handle that immense pressure. Now, when you're on site, your first check is that S stamp. It's your absolute non-negotiable proof of certification. From there, you're tracing material certs, witnessing the hydrotest, and verifying every single welder's qualifications. Now, let's switch gears to a totally different kind of boiler. Section 4 covers the low-pressure heating boilers. The kind you'd find in a big commercial building. The whole risk profile here is completely different. Instead of containing massive, explosive potential, the focus shifts to making sure it operates safely and efficiently. And that's exactly why the key formula here is boiler efficiency. Your site checks reflect this, right? You're testing safety valves, checking burner alignment, and confirming integrity with a hydrotest. It's all about safe performance, not just brute strength. And now for Section 8, which covers unfired pressure vessels. So think of things like air receiver tanks. Here, the one number that matters most is the MAWP, the maximum allowable working pressure. This number is everything. It dictates the vessel's absolute safe operating limit, period. When you get to the site, your first stop is the nameplate to verify this MAWP. Then you're going to dig into the design records for joint efficiency values, review the radiography films to hunt for any hidden weld defects, and then you witness the final proof, the hydrotest. So, we've got the rules for the equipment itself. But how do we actually guarantee it's built correctly? Well, that comes down to 3 essential pillars that form the core of quality fabrication: using the right materials, having qualified welding, and doing rigorous inspection. It all starts with a material, and that's governed by ASME Section 2. This code is basically a massive library of material specifications. For any material you can think of, it defines its DNA, the required chemical composition, and its mechanical properties. On site, your job is all about traceability. You have to match the heat number on a piece of pipe to its material test certificate, the MTC, which is essentially the material's birth certificate. And for the final on-the-spot proof, a positive material identification, or PMI test, which confirms the material's chemical fingerprint right there. Next up, welding, which is covered by Section I-9. Now, what's really interesting about this code is that it doesn't actually teach you how to weld. Instead, it tells you how to prove your welding is repeatable and sound. The WPS, or Welding Procedure Specification, is like the recipe for the weld. It details every single variable. The supporting PQR, the Procedure Qualification Record, is the proof that you successfully cooked that recipe once in a controlled test. So your job on site is simple but absolutely critical. check the welder's ID, make sure that exact recipe is available and being followed, and then, of course, inspect the final work.
So how do we inspect a weld without cutting it open? That's where Section V, non-destructive examination, comes in. It's the rulebook for methods like radiography and ultrasonic testing, or UT. And this is just brilliant engineering. With UT, we're sending sound waves through solid steel and analyzing the echoes that bounce back. It's like having X-ray vision for metal, letting us hunt for hidden cracks or flaws that could cause a failure years down the road. As the QA/QC engineer, you are the gatekeeper. You verify the technician's certification, you check their equipment calibration, and you meticulously review their final report.
So far, we've been covering standard industrial applications. But now, we're about to level up. When it comes to safety and quality, nothing, and I mean nothing, is more demanding than the nuclear industry. And that, of course, requires its own, even more stringent set of rules. Welcome to Section 3, Nuclear Components. In this world, every single detail matters. The designs are based on a much, much higher safety factor because, well, the consequences of failure are just unimaginable. For something like a reactor vessel, the verification process is exhaustive. The single most critical element is the QA audit trail. You have to have a perfect, unbroken chain of documentation for every material, every weld, every inspection, all the way from the steel mill to the final installation. There is absolutely zero room for error. Wow, we've covered a lot of ground. So now let's pull all this information together into a practical, step-by-step workflow you can actually use on your projects. This is how you apply all those ASME codes in the real world. Okay, here's how it all comes together on site. It begins the second that material arrives. Step 1, you grab that shipment of pipe and immediately check its MTC. That's your direct link straight back to ASME Section 2. Next, before a single welding arc is struck, Step 2, you verify the welder's qualifications and make sure the correct WPS is right there, satisfying Section 9. Then, as fabrication gets going, Step 3, you're witnessing the welding and checking dimensions, following the rules of Section 8. After the welding is done comes inspection. Step 4, you oversee the NDT crew and review their work based on the procedures in Section 5. Step 5 is the final proof, conducting the hydrotest according to Section I or 8. And finally, Step 6, you compile all of this evidence, every report, every cert, into the final QA/QC dossier. And this brings us to the final output. And look, this isn't just a big pile of paperwork. It's the proof. It's the complete story of that equipment's life and its quality. By meticulously following this workflow and connecting every single physical action back to a specific code requirement, you produce what we all want, a safe, fully documented, code-compliant piece of equipment that is ready for a long and reliable service life. So there you have it, a blueprint for navigating the entire world of ASME. We've gone from the very fundamentals to the most stringent nuclear standards and wrapped it all up with a practical workflow. The only question left is, which one of these powerful tools are you going to put into practice on your project tomorrow?